In this video, we are introduced to vector spaces. This is chapter 4.2. So our objectives for this section are to define a vector space and recognize some important examples of vector spaces. We are going to be able to show that a given set is not a vector space, and if I give you a set, you're going to be able to verify if it's a vector space or not. Theorem 4.2 from chapter 4.1 listed 10 properties of vector addition and scalar multiplications in Rn. However, there are many other sets, for example, Cn, which is the n dimensions of complex numbers, sets of matrices, polynomials, and functions besides Rn that can also be given suitable definitions of vector addition and scalar multiplication, so that they too satisfy the same 10 properties. So in our branch of mathematics linear algebra, we can study all of these different possible vector spaces. So you aren't just limited to the vector spaces I listed. People very often come up with vector spaces. So in this example below, from a research paper published by Stanford University, here's a vector space model for XML retriever. So you can see the mapping of the XML document on the left to a set of lexicalized subtrees on the right. So you can see it is possible to come up with all sorts of vector spaces when you're creating models. So here's a definition of a vector space. We're going to let V be a set on which two operations, vector addition and scalar multiplication, are defined. If the axioms listed below are satisfied for every U, V, and W in this set V, and every scalar C and D in a given field, usually our field is the real numbers or the complex numbers, that F with the lines is how we represent the fields. Similarly, the V is how we represent a vector space. So if the axioms are satisfied for U, V, and W in our set V and scalar C and D in usually either the real numbers or the complex numbers, depending on how we've defined it, then V is called a vector space over field F. So F can be the real numbers, which is what we'll deal with most often. It could be the complex numbers, or we'll see there are some other possible fields. The 10 properties, or the axioms as we say, that need to be satisfied are first, closure under addition. So the sum of the two elements U plus V have to also be in that same set V. Lowercase v here, U plus lowercase v has to be in the capital V set. The commutative property has to hold. U plus V has to equal the same as V plus U. The associativity property has to hold, so we can add in any order. So remember, our operations here are vector addition and scalar multiplication. Fourth, we have the existence of an additive identity. So V has to have a zero vector such that every U in V, if we do U plus 0, we get U back out. And there has to be an additive inverse, or what we think of as an opposite. So every U in V, there needs to be a vector denoted by negative U such that U plus negative U gives us the 0 vector. The sixth property is closure under scalar multiplication. So scalar multiplied by vector V has to also be a vector in V. Distributive property over vector addition. So C, the scalar, times the sum U plus V has to also be equal to C times U plus C times V. The distributive property has to hold over scalar addition. So if you've got scalar C plus D in parentheses multiplied by U, then that has to equal C times U plus D times U. And then the associative property has to also hold for scalar multiplication. So C times the product du in parentheses has to be equal to the same result as if we multiplied C and D first and then multiplied that by vector U. And then the scalar identity holds. So for scalar identities, that's saying the scalar 1 multiplied by the vector U gives us the same vector U. So it's important to realize that a vector space consists of four entities: a set of vectors, a set of scalars. So our set of vectors are what we're saying are u, v, w, and our set of scalars are c and d here. And two operations. So the operations are vector addition and scalar multiplication. So when you refer to a vector space V, be sure that all four entities are clearly stated or understood. And then unless we've stated otherwise, we're going to assume the scalars are the set of real numbers. So if you want to think of the scalars as the complex numbers, be sure that you state that. All right, so notice, oh, here's my same note. Notice the vector set actually consists of these four entities. All right, so let's look at some examples of vector spaces in the next few slides. So unless I say otherwise, we're assuming the field is the real numbers. So think of the plane R2 with the standard operations. So we know u plus v equals the component-wise addition. We know a scalar multiplied by u is a scalar multiplied by each component. We know the zero vector is the origin 0, 0. And we know negative u is negative on each component. So that's a vector space. In general, Rn, the n-dimensional real numbers, with the standard operations is a vector set. So note that this includes R2, which is just R with the usual addition and multiplication. The complex numbers, so Cn, the n-dimensional complex numbers over the field of complex numbers with the standard operations, is also a vector space. Here are some more examples. So the vector space M23 of all 2 by 3 real matrices with the standard operations. So if we check here, A plus B, each element inside the matrix gets added up component-wise. So you can see we meet the vector properties. And we know that the elements in the matrices can be added in any order. So we've got our associativity property. We know the commutative property holds. We know there's an additive identity for matrices. And then we also know if you multiply a scalar by a matrix, that scalar gets multiplied by every entry in the matrix. So it's also closed under scalar multiplication. So in general, the vector space of all m by n real matrices with the standard operations are considered vector spaces. The vector space P2, so we do a subset 2 to tell us the degree of polynomials. So this vector space P sub 2 of all polynomials of degree 2 or less with the usual operations is a vector space. So if we let P equal a naught plus a1x plus a2x squared, and q equal another second degree polynomial, b naught plus b1x plus b2x squared, where the a's and b's are all coefficients. It can be any real number. Then we can define our usual operations for polynomials. We know if you add the coefficients and then multiply them by each element of x, that's the same as if you added up the two polynomials. And then we know if you multiply the coefficients, that's the same, well, not the coefficients, if you multiply the scalar, that's the same as if you multiply a scalar outside the polynomial. So we know you can multiply a scalar by any element inside the polynomial, and you get the same thing as if you distribute the scalar through. So let's verify closure under addition here. So if we've got P plus Q, that's saying polynomial P of X plus polynomial Q of X. And so that's going to be each element of P of X plus each element of Q of X. And then we know we can pull the coefficients together. So we've got A naught plus B naught, and then we've got plus A1 plus B1 grouped together multiplied by X, and then A2 plus B2 grouped together multiplied by X squared. So this is still a polynomial of degree 2. It would be less if A2 plus B2 was 0, if they canceled each other out. So notice that we have used the commutative and distributive properties of the real numbers, and then you can go through and verify the other axioms in a similar way. So note that the 0 polynomial in P2 is 0 plus 0x plus 0x squared. So because when we did our addition here, our subsequent result was still a polynomial of degree 2 or less, we say, okay, we're closed under addition because when we add up the polynomials, we're still in that same vector space P2. There's no way to add up second degree polynomials and get a third or fourth or higher degree polynomial. So you couldn't multiply the polynomials and consider it a vector space. That's why we are closed only under addition of the polynomials and scalar multiplication. But if you were to multiply the vectors, you would leave the vector space. So in general, the vector space Pn of all polynomials of degree n or less with the usual operations is a vector space. And then if n is 1, the vector space P of all polynomials with the usual operations. All right, here are some more examples of vector spaces. So remember, when we check to verify things are vector spaces, we're checking vector addition and scalar multiplication. We're not necessarily multiplying the elements of the vectors. It's just adding the vectors and multiplying through by a scalar that we stay in that same vector space. So now we're going to talk about the vector space that we denote C from negative infinity to infinity. And so that's the continuous real valued functions on the domain from negative infinity to infinity. So that capital C, if you remember from calculus, that tells us it's a continuous function set. So for example, if you've got x squared plus 1 that is graphed over here, the parabola, here's f. If you've got 8 over 1 plus x squared, sine x and e to the x, those would all be vectors in the continuous real valued space because they're all continuous functions that go from negative infinity to infinity. They don't have endpoints here. So over here on the graph to the right, we've got a function f that I circled in green, and then we've got another function g that is here. And then we are going to show that if you add f and g, you're still going to be a continuous function. So if you can imagine here taking like the height of f and adding it to the height of g, you get this new height f plus g of x, adding up the functions. And so this whole top curve up here, I'm not very good at highlighting it, but I'll try to highlight it and show you here in red, is the curve we get when we add up every point of f and g. So this is f plus g, and you can see it's still a continuous function, and it still goes from negative infinity to positive infinity. It doesn't have any endpoints. There's no holes. It's still continuous. And then similarly, imagine if you took f and multiplied it by a scalar, you'd still have a continuous function. It would just be stretched or potentially flipped depending on your scalar. But because we're from negative infinity to infinity, we can include any flips or rotations. So then we say f, g, and f plus g are vectors in this space of continuous real valued functions on the domain negative infinity to infinity, just in the same way that u, v, and u plus v are vectors in Rn. So f can be thought of as a component. F of x can be thought of as a component of f, just as u sub I is a component of the vector u. So u has n components, u1, u2 through un in n dimensions. And then our function f has an infinite number of components because you could put in any particular x value there. So you've got infinite choices because this is a continuous line, right? Infinite points on a continuous line or curve. The additive identity, the zero function, is going to be f sub 0 of x equals 0. So that's the x-axis when our y value is 0. Because if you take a function and add it to 0, you get the same function. And the additive inverse is going to be negative of the function f of x, because those would zero each other out. All right, another example of a vector space is the set of continuous real valued functions on the domain AB over the real numbers. So if you've got, notice that AB is closed here. So if you've got a closed space here, you can have a vector space here following the same rationale as we saw for the continuous real value functions on the domain negative infinity to infinity. It is important that A is not equal to B, because then you would have not really a space. So any closed interval, as long as you've got a beginning and an ending. Obviously, this wouldn't work for an open interval because you could add up elements and exceed the closure points. All right, so we will continue in the next video with looking at properties of vector addition and scalar multiplication and some examples of spaces that are not vector spaces.